welcome everybody at this QuMat seminar. Today we have a speaker, in-house speaker, Lars Fritz. He doesn't need too much introduction, I think, but he's a general coherence matter theorist, I would say, working on many topics like topological insulators, high temperature superconducting spinches, and all the general array of problems in coherence matter. Maybe he's mostly well known on his work on Congo problems and multi-channel problems. And he has also worked a lot on graphene and the hydrodynamic regime of electrons. And I think that last part is more close to the topic of today. So I give you the floor.
Okay, thanks, Henk. Yeah, welcome. I've given related talks, I think, also more or less in this institute or in adjacent ones, but I don't think ever to this audience in particular. So I will be talking about novel insights in transport properties of 2D metals. This will mostly be theoretical, so apologies before we start. There's an array of, so this talk actually has quite some history and build-up, and there's an array of people that I worked with over the years, and also locally, like Henk, he's one of them. I would still like to highlight two in particular, like Emanuele, with whom I'm working on essentially extensions of this. Like you don't get the very latest version, so there are extensions. And I also want to particularly highlight Kitinan from Sangangan, who was a PhD student here and who did. It's fair to say he did most of the very technical stuff in this project, or in this version of the project. So we're talking about something, essentially, like the whole subject is something extremely basic. It has something to do with metals. In particular, this will be about 2D metals, but it's actually more general. And there is a standard model of metals that is commonly accepted in condensed matter physics. It's called Fermi-liquid theory, or the Fermi-liquid. And the idea is actually, the result is very simple, but the idea is quite complicated. And so the idea is to have all these electrons in your system, in your condensed matter setting, for instance, and they come from the atoms, and somehow, and they interact. There are Coulomb interactions between them, Coulomb interactions with the atoms. So it's an extremely complicated system. But after everything is said and done, the end result is quite disappointing in some ways. So Fermi, or also Landau, who was like another name you should mention in this context, they concluded that after everything is said and done in metals, what you end up with is something that you call a quasi-electron, which is not the electron, but it's rather the original electron, including all the renormalization effects taken into account. But after that is done, it behaves for practical purposes like an electron. And there are small corrections to that. And yeah, so one thing you see here is there are these words like liquid, sea, and they all are reminiscent of fluids. Fluids, they actually flow. And I think one of the questions that, or one of the questions I want to address in this talk is, how do electrons in a metal, how do they actually flow? So what are the theories about that? And maybe also what are the open questions? Okay, so first of all, like when we talk about flow of liquids, we have something like this in mind. Like this is a creek, and there's water. It's flowing along, and this type of flow is like it's a collective effect. So you would never talk about, say, the flow of an individual molecule, but it's really a collective effect, and it's dominated. I will talk about this in more detail by conservation laws. And there's also all kinds of other effects like turbulences. It can have whirls, etc. And now also when we talk about like electronic transport, electricity, for instance, we also use these words like flow, often very loosely. However, if you open a textbook on electronic transport, or in general on condensed matter theory, let's say you open one of the introductory ones, you will find often there's a discussion on the Trude model, and there you will find a very different picture. Like there you will find a picture of essentially individual electrons that are moving around and they're bouncing against stuff, which hinders their motion. So you can see here there's collective, there's a single particle property, and this is mostly diffusive behavior. So from the point of view of flow, this has very little to do with the liquid. Okay, so I will try to be more precise about this in a second. So hydrodynamics, which is the theory of like how liquids flow, it was introduced to describe the flow of classical fluids, such as water, for instance, which you see here. And it has some basic underlying ideas. And one very important one is that of local equilibration. So you have a system that is locally in thermal equilibrium, and conservation laws. For instance, for classical liquids, you would talk about conservation laws of momentum, energy, mass, for instance. What's also important is that this local equilibration takes place on a scale that we can call that the equilibration scale. So and this depends on details of the interactions in your system. So importantly, since we're talking about conservation laws, we can only talk about interactions that respect those conservation laws. So interactions or effects that don't respect those conservation laws, they can still lead to equilibration, but they would violate this. So you need both. So you need a dominant equilibration scale, and you need it to obey or to fulfill conservation laws. And then you can derive all these things that you know from textbooks, like Navier-Stokes equation, continuity equations, etc. Now let's zoom in a bit more in this flow of electrons in metals.
I don't think you need local equilibrium to have a flow, hydrodynamic flow.
How do you mean?
I mean, you can have a distribution that is far from equilibrium at the microscopic level and still have a hydrodynamic limit.
Not sure I understand what you have in mind here. So I mean,
well, in cosmology, you have a distributions that are far from equilibrium, for example, that matter.
okay.
And they distributed in equilibrium, non-equilibrium, we don't actually know. Decided because they have a similar hydrodynamic behavior, independently.
But there's no notion of local equilibrium in that?
No.
No? Okay.
No, you just have a distribution, whatever it is. And this distribution is then characterizes the density, energy density, and fluid velocity.
So that's how you get your density.
There are integrals, right? So there are microscopic quantities, and then these flow, right? Local equilibrium is not a condition.
Okay, I can see what you're saying.
Yeah.
Okay. Okay, so now let's look at this one in a bit more detail. Now, in metals, so it turns out metals are actually horribly complicated objects. So besides the interactions that I mentioned, there are all kinds of other things. I mean, maybe I should be more precise here. What I have in mind, like there are Fermi liquids that are not in the, let's say, lattice setting that I have in mind. But for the ones that I have in mind with this lattice setting, there's a set of complications. And metal, like these systems in particularly, they have many scales. So for instance, they can have, there can be geometric scales like the width of your sample. So I should also say I'm mostly interested in transport properties here eventually. And these are the things that usually pop up there. Okay. Then there are, and these are the most common, things, or it's usually the dominant effect. There are impurities in your system. And there are, since we have the lattice, there are also lattice vibrations. So these three are, if you want, like external factors which come from outside the electronic system itself. And then there's an internal one, which is electron-electron interaction through Coulomb interaction. Okay. And you can ask questions about like what conservation laws are actually disobeyed or obeyed in specific processes. Okay, for instance, when we're talking about impurities, then these impurities, they conserve mass or charge if you want, or scattering events within. They conserve energy, but momentum is not conserved. So they break momentum conservation, which is one of the key ingredients of hydrodynamic behavior. We have the aspect ratio here, for instance, same story. Momentum conservation is disobeyed. The reason is simply because translation symmetry is broken. Phonons, which are the lattice vibrations, they're a bit more tricky. So usually there's no problem with charge conservation, but phonons, they can take momentum and energy. And somehow, and this is the key here, they can take momentum and energy out of the electronic system and dissipate it in their own subsystem. Okay, and then there's electron-electron interaction, which essentially conserves all of that, which we want, like, which is important for hydrodynamic behavior. Now, usually, the hierarchy in condensed matter metals is such that the impurity, like the mean free path or the equilibration length due to impurity scattering, is the smallest and thus dominant one. This is usually the one which determines the behavior of the system at low temperatures. Then there are phonons, they are usually a bit less important, and then electron-electron, which is often totally subdominant. Now, if you're interested in hydrodynamic behavior, you would actually want this to be the shortest scale, which means you have to knock out the other scales. And you can now say, as a theorist, you can say words which are very simple for us to say, which are very hard for experimentalists to make, like you just have to make the perfect system, for instance. Phonons is a bit trickier, but anyways. Okay, so, but what, like, a main issue, it really is that these systems are usually too dirty, or traditionally too dirty for this to happen. Okay, so yeah, we want an equilibration scale LEE, which is dominant. Now, in this presentation, or the remainder of it, rather, I want to touch on one question, which is like, what is the hydrodynamic theory of metals? I will be a bit more precise in a second. And related to that, what are the transfer properties of very clean metals? Because obviously, like if we want hydrodynamic behavior, system has to be clean. Then we have to ask the question, what is the transfer property of a clean metal? Obviously, they are connected. And also, I want to touch on one aspect, which is that there is actually quite a strong difference between 2D versions of metals and 3D versions. And I think this has become quite apparent in recent years, mainly because experimentalists have become so good at making 2D metals. And so you can really look at these 2D metals now. But, graphene, obviously, the most prominent one, but there are many others. I will also touch on this, because I think some of the things I will mention are people were actually studying in the 1960s, and they were not looking at specific details, mostly because this was not even something they were thinking about. After that, some of the questions were essentially decided to be settled. And people forgot that there was kind of an asterisk which said, like, yeah, we're talking about 3D metals and not 2D. Okay, there's like I already said, there's a different way of looking at this thing, and one of them is I will touch upon what are actually the degrees of freedom that enter the hydrodynamic description, because the hydrodynamic description itself is kind of fixed. But you can ask, like, what are the densities? What are the important densities in the game? I will talk about how all of this connects to transfer properties, and there's a particularly important one, which is the ratio between electrical conductivity and heat conductivity, which is goes by the name Wiedemann-Franz ratio, or there's this Wiedemann-Franz law. I'll talk about that. And I will also talk about this 2D versus 3D, and there's a very technical version of what we were doing, especially with Henk, which is how to do a proper conserving approximation in these systems. Okay, now this is like the next 2-3 slides are the only experimental references I have. So the first one is there's actually, in particular in the context of graphene, there has been a series of recent experiments, let's say last 5-6 years, and some of them have been recognized as being related to hydrodynamics, others not so much, and I think I will try to give you an idea why. So one of them is essentially, it's about systems in confined geometries where experimentalists manage to map out flow profiles of electrical currents. I have on the next slide, at least I can show you some of what this looks like. And I would call that boundary effects or boundary probes, and they are mostly like they're actually probing this thing viscosity, which is a measure for momentum transfer between adjacent fluid layers. And there's a second class of experiments which I would call bulk experiments, which are like essentially you're looking at big systems and you're making transport experiments. And this is something where, in principle, you don't really expect hydrodynamics to be visible to the eye, mostly because it's unclear how viscosity should manifest itself. But I will give you a picture in which it naturally emerges. So this seems hopeless, but there are actually very specific systems in which you can access those regimes. Okay, now those are like more or less recent, already a bit dated, but still relatively recent experiments in confined geometries where experimentalists managed to measure flow profiles that are characteristic of hydrodynamic flow. For instance, they have a parabolic shell. Since I'm not super familiar with the experimental details, I will try to be fast here and hope nobody asks any questions. But yeah, so these are the two most important papers. And yeah, again, I think the key here is they're sensitive to viscosity. So now, how about bulk? So like a bulk, let's say from a point of view of a theorist, like bulk is just like some massive blob. And we're connecting, for instance, here we're connecting source and drain. And in some ways, you would expect something like a homogeneous flow profile in such a situation if you have a flow. So there's no obvious room for viscosity. There's actually another reason why this seems like not a great setup in general, which is related in the end, which is that if you think about electric transport, what it does is you take an electron, you apply an electric field, and your electron gets accelerated. And unless there is something in your system that allows the electron to lose momentum, it will just continue to be accelerated. Okay, so you would actually, in a bulk system, it doesn't sound very likely that you would end up with the finite conductivity in that situation, because there's no effective velocity that is finite, which can be established by losing momentum to the system. Okay, so this, long story short, what I was trying to say is that in such a system, even if you have strong Coulomb interaction between the particles or the electrons in your system, you still expect that the transport properties are actually limited by disorder, because that's the one which relaxes momentum or current. Okay, which also means like you might actually be in a hydrodynamic regime, but a transport experiment would not tell you. Okay, but now there are, for people who work in graphene, they might already get an idea where this is going. There are other systems where, like by some magic, you can't just have electrons, but you can also have holes, which are positive charges. Okay, and now if you apply an electric field, you will have a situation where they're actually dragged in opposing directions. Okay. And now there's room for viscosity, because now you have a profile. And if these two, they interact with each other, which they do by Coulomb interaction, then you can actually establish finite current, provided they come in equal size. So in equal amount. They have to come in equal amount. The moment there's an imbalance between the two, you will induce a net momentum. And then you need disorder again. Okay. Now, the situation I described is, for instance, realized in graphene. So if you talk about graphene, then what's characteristic is there's this charge neutral situation in graphene in which the system is perfectly particle hole symmetric, and it has a density of states that is 0. Okay. Now, what happens at finite temperatures is actually that you're inducing a thermal density of both electrons and holes. Essentially, those are just the consequence of the missing electrons that sit here. Okay. So you're inducing finite concentrations of electrons and holes. And now, if you're using these finite concentrations, you can apply an electron. So maybe I should position this a bit more clearly. So in the early days of graphene and the study of transport, especially in charge neutral graphene, there was a discussion about something called the minimal conductivity, universal conductivity. And one of the hallmarks of this discussion was that there was huge disagreement on what the electrical conductivity of charge neutral graphene is. And it turns out the reason for this disagreement is mostly that the question by itself is extremely badly defined. So it turns out that depending on how you string your calculation together and how you take limits, you can actually get anything from 0 to infinity. So it's not continuous, it's more like they're discrete points, but you can cover the whole range. Simple example, if you forget about Coulomb interaction, you're at finite temperature, you have these two clouds, you have no disorder, because there was always this, the statement was it's independent about disorder, thus it's also true for the clean case, etc. If you have no disorder, no Coulomb interaction, you're at finite temperature, then those things would just fly apart, conductivity infinite. If you're at 0 temperature, on the other hand, there's simply nothing. So conductivity 0. And then you can do all kinds of things in between. Like disorder, for instance, would induce finite densities of states, and then you end up with something finite. And so it really depends, crucially, on how you take limits in your calculation. Okay. However, it turns out there is one of them which is actually well-defined. So there's one limit which is extremely well-defined, which is the one when you add Coulomb interaction into the game. And now everything is finite, and I will show you what it actually is. Okay, so the model that you're discussing is now just Dirac fermions that are interacting via Coulomb interaction. Okay, now Coulomb interaction in graphene is actually a funny one. Because graphene plus Coulomb interaction looks a lot like QED, but it's not. So it looks a lot like QED in the sense that you can define something like a fine structure constant. However, there's a big difference here, which is this fine structure constant. If you compare it to QED, it's actually bigger by a factor of almost 300. I'm forgetting about complications like substrate, etc. at this point. So if in QED you have something like 1/137, blah blah. Now, which means here you're essentially in the range 2, and then you have dielectric effects which usually bring you here. So I think the bottom line is this is by no means guaranteed to be a weakly interacting problem. You have a dimensionless parameter that's essentially 1. Then usually perturbation theory shouldn't be your first choice.
But it is also dope independent. It's very strongly dope independent, right? I mean, there is these experiments by Andrew Guy where he shows that the Dirac column gets heavily renormalized and it becomes something like this.
It's logarithmic still. I think I think the scales are exaggerated.
So this alpha is a function of density, and it spreads like that. So it's very strong.
I mean, it's this thing with the suspension, right?
There are different kinds of measurements on different kinds of substrates.
I mean, but usually
that to renormalize is very strongly.
Well, it's logarithmic. So
no, not only. The VF depends on N also.
Well, that cuts it off, yeah. Okay. But still it depends on N in the logarithm. So that part doesn't change.
Okay.
So I mean I know the plots, but they were made with the loving eye of a father, I guess. So they, yeah. So
I mean, it's very different.
Yeah.
When you don't take this log into account and when you take it, you see the difference.
yeah, okay. We can agree there is a renormalization, I guess.
Yes.
I wouldn't say it's extremely big for practical purposes. Yeah. Okay. Great. So you can question the use of pure perturbation theory. Importantly, though, you're actually conserving everything that we said was important for hydrodynamic behavior. Okay, so to keep an eye on time, I'm not doing great. So the thing here is now you can calculate this electrical conductivity. And the standard weapon of choice is the Boltzmann equation in this regard. And we actually did so in two types of systems. One of them is the normal graphene, and the other one is bilayer graphene, but not the twisted one that people talk about a lot these days, but the say the more basic one, which has two layers that are have a regular stacking and have this parabolic dispersion. Okay. Now you can, like, there's essentially you're doing the same calculation for both of them. This one is a bit more complicated than this one, and you find that there is a minimal conductivity now in. Actually, I should mention we do perturbation theory. So this is purely perturbation theory. Okay, so we do perturbation theory, and we find that there is this expression, sigma is 0.76 E squared over H times 1 over alpha squared, where alpha squared is the fine structure constant. And there were measurements, like in this paper. So this number here is what you get from the Boltzmann equation. This is just from some complicated integral. And there were recent measurements, again, like recent meaning 5 years ago, and they found something that agreed with this expression when you replace alpha with 0.21, which was in good agreement with the dielectric constants that they have.
This was silicon oxide?
No, this was boron nitride.
Boron.
Usually in this, let's say in this business of ultra clean graphene, they use boron nitride because they get it cleaner. Okay, and then there's the bilayer, and again, so you can make a calculation based on the Boltzmann equation, and there were two papers independently, like one of them, that's the older one from 2017, in the group of Morpurgo, and they found they made several, like they had several flakes, several sizes, etc., and they found numbers that were consistent, say in the range between 12 and 24. So that's not a minus, that's a range actually. Like so 12 to 24 E squared over H. Okay. And then more recently, there was a paper, or there was an experiment by Hohn in Singapore, and they found relatively consistently 25 E squared over H. So what's actually interesting here is if you look at this, this looks extremely universal. There's nothing in there. Like it's just E squared over H. It's basically like quantum Hall in some ways. Not as good, of course. But. And like the theory result is 27. So which, given that we're doing second order perturbation theory, I mean, you be the judge. I think the agreement is great, but maybe one shouldn't over-interpret it. Okay, now, in both of these works, what we did was we actually gave the interactions one simple role, and that was local equilibration. They were just equilibrating stuff. However, it turns out that in principle, in electronic systems with interactions, we know that more can happen. Like I advertised in the beginning, there's this Fermi liquid theory, which is essentially a theory of only electrons with small corrections. It has some instabilities, like maybe superconductivity, but in principle, it's a theory of electrons with some renormalization. And this has been studied, as I said, up to the 60s, and there are many, many names. There's Fermi, there's Landau, there's Bohm, there's Abrikosov. And essentially, the story was, as I just said, there are electrons plus small corrections. Okay. Now, on the other hand, it is well known and established that if you go to one dimension, taking into account interactions between electrons leads to a very different picture. It's what's called the Luttinger liquid picture. That's essentially where Dirk lives. So Luttinger liquid is characterized by the fact that the elementary excitations in this system are, in fact, of bosonic nature and collective. So an effective low energy description of the systems doesn't really involve the electrons as elementary degree of freedom, but it's really about collective effects. Okay, and now obviously it's kind of suggestive to us. So what actually happens in 2D when you write at the end, like when you write in the middle? So here it's only electrons, collective modes play basically no role. Here it's only collective modes, electrons play very little role. So what happens here? Kind of suggestive that this should be the point where both of them fight some version of a fight here. Okay, so let's take one obvious one, which are charge oscillations, plasmons. And in three-dimensional metals, and this is actually why I think what I'm discussing today was not discussed in the 60s. So in 3 dimensions, you can look at the dispersion of plasmons, and you will find that they have a massive gap. So they have an extremely large excitation gap, which essentially means if you're interested in low energy properties of your system, they play almost no role at all. Okay. Now, this is true in 3D, but it's actually not true in 2D. So in 2D, if you look at the excitation, or if you look at the plasmons as an excitation in your system, you find that plasmons are in fact a gapless excitation. They have this square root of K behavior, and on top of that, they're very, very stable. They have almost no decay mechanism. So for practical, like, there's no reason why you should discard them a priori in any description that you make, any low energy description. Okay, I'll come in a second to why this might be, or why this is important. Okay. Now, as I said in the beginning, we're interested in transport properties of the metals, and there are usually 2 things that people look into. One of them is electronic transport, and one of them is heat transport. Essentially, how much energy can you transport between leads? And the standard theory that people apply in the field, and I'm sticking, like, at the moment, I'm really talking about graphene or bilayer graphene, something where you have electrons and holes. And the standard theory in this setup is or was that you would consider electrons and holes and how they react. Now, what if you want, like, if you're asking the question, so what's the main message of all I'm saying today? Then in some ways, this is it. So my main message here is that in principle, and you can actually, you should probably replace this more generally with collective mode. So in principle, if you look at graphene and its low energy or its thermoelectric transfer properties, a priori, there is no good reason to discard collective modes. Because A, we're not really weakly interacting. So it's really like alpha is actually a number on the order of 1. And B, and that's related in some ways. Well, not in some ways. And B, the plasmons are gapless. So for instance, what that means, like anything that's thermal should be able to excite them, transport them, etc. Obviously, the plasmons, they will not react, or they should not directly react to electric fields because they're charge neutral. Okay, now, like again, just to what's really important here is that the theories about the electrical transport that I talked about, they're actually not the very problematic ones. So what's really problematic is heat transport. And the reason is because if you look at this Hamiltonian, which is the full Hamiltonian, you have interactions here that directly contribute to the energy density. So they should matter for energy transport. Okay, now usually when people discuss thermal transport and they concentrate on the electrons and the holes, then they concentrate on this quasi-particle part of the on this electron and hole part of the energy current. But it turns out that if you derive the energy current properly, this thing will actually also make a contribution. But this is a very tricky one. If you look at this, this is really bad news because this is long range. So I mean, you can write down a contribution of this thing to an energy current, but it's very hard to do something reasonable with it because it has this non-local character. Okay, so now exactly. So there's some treatments, mean field theory. So people in the theory of D-wave superconductors, Patrick Lee, to name the most prominent one, they did some mean field treatments of these, where in principle you could already see that there is a contribution, but our point here is not about mean field. We actually want to do one better. And this naturally, interestingly, this naturally leads to the plasmons. Okay. Again, like in 3D metals, Böhm and Aprikosov, they were aware of that, and they concluded that it's unimportant simply because the plasmons are kept. Now, the good news is that we have Henk's book. And if you look into Henk's book about interacting systems, you will find that there is a trick that you can use to convert an interacting problem, like for instance here the interaction is between densities. You can convert this one, and this is a complicated problem. You can convert it into another complicated problem, but one in which you can write something that is non-local as something that is local. And this is called the Hubbard-Satonovich trick. And the strategy there is that you essentially replace one of these densities with a field, like with the and then you can. It's just like, in the end of the day, it's just completing the square. So it's just completing the square, and then you can get back here. Okay. Now, what's interesting is that you can actually, now that you have a local theory, you can use well-known machinery for, if you're interested in the energy current, for instance, you can use the Noether theorem in a straightforward manner. There's other ways in which you can do it actually, but okay, this is a nice one. And then you get an additional contribution now, which is due to these modes. And now this is where like I'm done with the very technical stuff in a second, but this is probably one of the most technical slides. So there's this scheme, which is called RPA, random phase approximation. And I think in particle physics, this would somehow translate to large N schemes, which is equivalent to this Hubbard-Stratonovich up to corrections to second order in the fluctuations around mean field. Then you get this set of equations. This is, if you look, you have two coupled equations. One is this collective field phi, and the other one are the original electrons psi, which are, in the case that I discussed, it's the spinors of graphene, and this is this mode phi that I introduced. Okay, and it was recognized, and this is very important for us. It was recognized in the 1960s by Kadanoff and Bain that this thing here constitutes what is called a conserving approximation. So this is one of the funny things about perturbation theory. Like when you do perturbation theory and you have a system with, say, translational symmetry and momentum conservation, then you can add up a series of diagrams that all individually conserve momentum, but the moment you resum it, what you get violates momentum conservation. So that was actually realized by Kadanoff and Bain. And then they spent huge effort into finding approximation schemes that conserve these things. Like another one that maybe you've heard about, which is related or which is similar in spirit, is Award identities, where actually also like you learn that you can't do perturbation theory naively, but you have to obey certain relations, for instance, between vertices and self-energies. So it's in the same spirit. Yeah.
So in this approximation, the eta field is treated in the 1pi approximation and pi field in the 2, in the sense that everything is linear in the double solid line. Right. So in the pi, it's not better.
I guess you're actually right. I think there's one line missing here. Yeah.
Okay, so this is really
Yeah.
yeah.
There's one line missing here.
Yeah.
Okay. Good point. Now, there are spectral properties related to these Dyson equations, and one of them is what Christiane mentioned. It's this logarithmic renormalization of VF on the level of the on the level of the electronic propagator. And this was already found many years before graphene, actually. Okay, and then there's the other equation, and the other equation is in fact the Blasmon equation. So what you find when you go through this whole strategy is that the other particle, the other field that I used to decouple the interaction actually turns out to be the Blasmon. Okay, and so I've already discussed the properties of that. Okay, now we're interested in transport, and so far I've discussed properties of the spectrum, but there's more to that. There's actually also what's called the quantum kinetic equation, or the Keldysh equation, and we also get 3 coupled ones there. Actually, it's 3 because we have electrons, holes, and plasmons. This one, even though it looked like 2, it's actually also 3 in disguise because this has 2 degrees of freedom. Okay, so they look like this. And the important thing here is that what you see here, these things, they have something to do with the spectrum, but there's one more ingredient here, which are called F and B, and those are distribution functions. And now we can go through a series of manipulations where, like, first we do a Wigner transform, a quasi-particle approximation. So this one actually, just to make that point, at some point I said that the plus ones, they are remarkably stable. Okay, so that statement is actually really important here, because we're making this thing which is called a quasi-particle approximation, where we pretend that the plasmon behaves basically like a particle. And the reason we're allowed to do that is because it's remarkably stable, if you look at it. So more technically, it has a very sharp spectral function. Okay, and then eventually you end up with a Boltzmann equation. And in this Boltzmann equation, this thing called B becomes, yeah, at least in equilibrium, it becomes the Bose distribution, and F becomes the Fermi distribution. Okay, so this is what it looks like if you want to calculate it. Yeah, it's actually pretty horrible. Like, you see, everything is coupled, and now I'm going through this with you term by term. No, actually, I'm not. But yeah, this is the kind of stuff that you have to deal with. Okay, so what's nice though is it's the basis for a couple of things. One of them is, like, you can derive hydrodynamic equations from it. You can derive conservation laws from it. You can identify, coming back to what Tom said, you can identify the densities, etc. So this you can even actually, I told you, you can use the Noether theorem to get this contribution to the thermal current, or to the heat current. But you can actually also do it on the left, starting from the Boltzmann equation itself, via the continuity equation. So actually, like, my favorite version of the derivation, to be fair. And we can use it to study transport properties in linear response. Okay, and this is the one that I will. Oh, I'm basically done. Okay, so I will try to hurry up here. So basically, schematically, like, when we made this calculation without the plasmons, or when people make the calculation without the plasmons, there's always structurally, there's something that is called there's something corresponding to the left-hand side of this Boltzmann equation, which is often called the driving term, or in at least if you talk about transport properties, because it involves these fields that actually drive the currents, like electric field or temperature gradient. Okay. And now, in this picture of electrons and holes, you have, like, the driving term for the electrons, one for the holes, and you have scattering integrals. So that's everything that was on the right-hand side was scattering integrals. Okay, and they are coupled. So you have this picture that I already had on the blackboard. Not on the blackboard, on the slides. Now, the new ingredient, technically, on a technical level, is this one. That if you add these plasmons, they also have a driving term. They come with, for instance, they react to temperature gradients. They don't directly react to electric fields, but they react to temperature gradients. And they come with the scattering integral. And now all of them are coupled. Which also means, like, there are, like, there's friction between them, there are viscosities, etc. Okay, you can check for things now. Like, what's really nice about the Boltzmann equation is that you can explicitly check conservation laws. So in that sense, that's actually the one thing in the paper with Henk that I think we did on top of what Karanov and Bain did in the 60s, which was that we actually derived these things. So they used Matsubara technique and general arguments. We could actually derive these things here. So, for instance, momentum conservation now is a statement of all these things adding up. The respective integrals. Energy, the same thing. Okay, so you get all the continuity equations, currents, and you can also think about versions of the Navier-Stokes equation. Probably generalized.
You also have conservation of high order moments, or no?
You mean like k squared, k?
You wouldn't.
I don't think so. I wouldn't know which. I mean, let's say if you're in the limit of only electrons and holes at the Dirac point in lowest order perturbation theory, you have some emerging. There's an emerging moment which corresponds to chirality. I don't think this one has an additional one. Depends on it, like, no, I don't think so. Okay, now the thing is, if you do this thing, follow this structure, you find that the energy current of the plasmons is actually given by the thing that you would phenomenologically write down. If somebody told you write down phenomenologically, like what is the energy current of a boson, that's what you would write down. So we did a lot of work for just getting what you would write down naively anyways. But fortunately, it was Kitinan who did it. So. Anyways, so okay, so that's the current. Now, yeah, in view of time, so we can study now all the transport properties. So this is the Onsager matrix, which has all these entries, sigma, kappa bar, which is related to the heat conductivity via this relation. And we can calculate them again from the Boltzmann equation. So you actually have to solve these equations numerically. So there's, at least we couldn't find anything to get it done analytically. And you can look at the Wiedemann-Franz law as well. So just one thing I wanted to mention here, which is that the Wiedemann-Franz law, if you're in graphene at the Dirac point and you're only looking at this electron hole picture, it's actually a really strange one, because the Wiedemann-Franz ratio at this specific point goes to infinity. And the reason is very simple. Like, the reason is very simple. If you apply an electric field, you have these counter-propagating densities of electrons and holes, and there's this viscosity friction between them, and that establishes a finite current, thus a finite conductivity. Now, if you apply an electric field, you have electrons and holes, and they both go the same way. So you induce a momentum, and Coulomb interaction cannot relax that momentum. So it's formally infinite. That's why the Dirac point is has a very peculiar property in that regard.
You said if you apply an electric field, you mean a gradient of temperature.
Did I say electric?
You said electric.
Okay, I meant gradient of temperature. Sorry. Yeah.
Yeah.
Thanks. Yeah, this one. Yeah, those are the two pictures.
Yeah.
Okay. Yeah. So, but I think in general, it's maybe worthwhile pointing out that the Wiedemann-Franz law is not really a law. So this is often taken as a sign of whether you have a metal Fermi liquid or not. And I know one example, which is the two-channel Kondo effect, where people in the field talk about a non-Fermi liquid, and you can actually solve everything exactly at this non-Fermi liquid point. And if you calculate the Wiedemann-Franz ratio, you get that of what's supposedly characteristic of a Fermi liquid. So I think the only case where you can make an exact calculation, you find a counterexample.
I'm just going to say it's my dubious honor to say that. Can you find a nice?
Oh yeah. I mean, I can just stop, or like I think okay. Okay. So overall, I'm actually there. I'm actually there. Like overall, in this system, now we have the following picture where electrical current is carried by electrons and holes. Then you have these plasmons, and what these plasmons actually do is they provide some source of scattering, but they're not really like actively taking part in electrical transport. only indirectly via drag effects. Okay, and then we have the thermal gradients and the heat transport, and that one actually acts on all of them. Okay, and for obvious reasons now, like one of the reasons Wiedemann-Franz law tends to hold in metals is because heat and electric current are carried by the same particles. And they are dissipated on the same effects. And now you can already see there's a mismatch when you just do the counting. So you should not expect the Wiedemann-Franz law to hold anywhere. Okay, and then you can make some more quantitative considerations. So what you see here is the chemical potential in graphene, which you can now tune. And without too much interpretation, like what you see is you can also make, for instance, you can study the heat transport, and you find that you can split off the electronic contribution from the total contribution, and you see some large enhancement due to these additional degrees of freedom. That also reflects itself in the Lorentz number. And this is something which shows the same thing. This is a calculation of the viscosity. This one is the one with the plasmons, and this scale is somewhat off. Okay. Okay, take home message. I think there are good indications that in 2D metals, because in the end of the day, almost nothing of what we did and that we only understood later is actually really characteristic of graphene. So it was just how we ran into it, but not much of it is actually characteristic of graphene. So take-home message is that in 2D metals, there are good indications that you can replace plasmons here by collective modes, that collective modes actually play an active role in transport properties and should not be discarded from the outset. And open questions there are a lot of them actually. And I think the biggest one at the moment is also what experimentalists have to say, because there's not really much data on that. And so if you have questions, like, let's stop it here. If you have questions about that, I can tell you more about it. But for now, let's stop it.
Maybe a few more. In the organic metals, the thermal power is formed by magnum drag thermal power. So I would say that even 3D there are instances.
Yeah.
Because the gap can be much smaller than
True. Yeah. Actually, yeah. I mean,
there's phonon drag as well. So now it's important.
yeah, for phonons, I kind of consider like forbidden to the game. Like, yeah. Oh, yeah. I agree.
And people have not worked out this size formalism is more like the vertical.
Yeah. No, I'm sure this is more like, I mean, there were also things like Kamran Binia, he was here beginning of the year, and he also talked about effects in 3D, which I believe are related to this.
I think the 2D effect is changes.
Yeah.
Small gap, which is
Yeah, I mean, Kamran said there are indications that you have bound states of collective modes that actually go soft. So even higher order, but I mean.
In this transport coefficient, have you tried to include also magnetic field?
What?
Magnetic field.
No.
Also magnetic field.
No. We haven't.
Any intuitions on that?
So we're probably not talking about quantum effects due to the Landau levels, I guess.
Well, I mean, yeah, but now I'm interacting field.
Yeah.
Some kind of response.
Don't really have a good intuition.
But in principle, you can just put it in your equation. No obstacle.
I mean, there are all kinds of problems with magnetic fields also because, like, there's this thing which is called magnetic catalysis, which is like you become extremely non-perturbative once you turn it on. Yeah, no, it's a good point.
Yeah, last question.
I wonder, what would happen to Darcy law in this world?
Sorry, what?
Darcy law. These are, you know what Darcy law is?
Can you like I've read Darcy, but I don't.
Take two plates
Yes.
and you have a certain viscous fluid there.
Okay.
Now you make a hole and you inject another fluid, and you see that the diffusion goes as fingering, and it's governed by Darcy law. And this is purely classical, and I would be very curious to understand what would happen here. It is basically how two fluids with different density will diffuse into each other. That could be very interesting to understand.
I have never thought about that, so I have no.
So we look at that.
I have no off-the-cuff intuition, but okay. I mean, I will look up Darcy law and.
In hydrogenated with thin.
Okay.
Where they could observe some kind of fingering. It could be very interesting to understand this in a hydrodynamic context.
Okay. No, I will have a look.
Yeah.
Okay, then maybe use time. Thank you very much
Yeah.
again.
Thanks for.